All right, so let's go ahead and prove the mean value theorem, which is sort of the generalized version of Rolle's theorem. So the mean value theorem, here, let me state the theorem. So this is 29.3. Let f be continuous on a b and differentiable on a b, then there exists an x in the open interval ab such that f prime of x equals f of b minus f of a over b minus a. So this, right. The reason it's called the mean value theorem is because this is considered the average rate of change on, I guess, AB. So this is just like the slope of a line that connects, the point on the graph at x equals a to the point on the graph at x equals b. So it's just like, rise over run basically. So like here, let me draw a picture. So, let's say here's oops, hold on. So here's the x-axis, here's f of x. So let's say this is a, this is b, and I don't know. Here's f of a, here's f of b, and let's say that's what it looks like. And then we have a straight line. We could draw a straight line connecting these 2 points, right? So this is like a f of a, and this is b f of b. So the slope here is f of b minus f of a over b minus a, right? And if you look, we can find these points kind of like, oh, that looks a little bit off, but something like that. Oops, it's also off. Something like that, right? Places where f prime of x equals f of b minus f of a over b minus a. One intuitive way I have of thinking about this is just like, if you imagine that this never happened, then basically, like, if you pretend, so the reason this doesn't work is because the derivative does not have to be continuous, even though f is differentiable. Even though f is differentiable at like every point, f is differentiable at every point on the open interval AB, the derivative does not have to be continuous. But if we just pretend for a sec that the derivative is continuous, right? Like in this example, the derivative is obviously continuous, okay? So that's kind of like the most familiar, like when the derivative isn't continuous, something like really messed up is happening. So if you just sort of pretend for a sec that that's not happening, if the derivative is continuous, then basically if you pretend that it never equaled this average, quote unquote, average value, then it would either always have to like be strictly bigger than the average value or strictly smaller than the average value. But then in either one of those cases, right, if you were to like integrate the function, then the function would be growing faster than it's supposed to, or slower than it's supposed to, and it wouldn't end up at having the value f of b once you get to b, right? So that's kind of the problem. Another way of thinking about it is like, if there's a place where the slope is bigger than the average, then there should be a place where the slope is smaller than the average. And so somewhere in between there has to be a place where the slope is equal to the average. But another way of seeing it is just, if you just kind of like tilt your head a little bit, then, oh, it actually looks almost exactly like the picture I drew for Rolle's theorem, right? So basically, that's actually what we're going to use, and it's not really so much rotating as it is actually shearing. If you shear the picture, so if you kind of like slide it, you know, it's hard to describe exactly what, you know, I don't know. Look up what a shear transformation is. Basically, what we're going to do is we're going to subtract a linear function from this, from the whole sort of picture and turn it into Rolle's theorem. Okay, so the idea is it's like we want to subtract a constant from the derivative of f. Okay, namely, we want to subtract this constant, f of b minus f of a over b minus a. We want to subtract that constant from the derivative, so that way we just need to find a place where the shifted version of the derivative equals 0, right? But subtracting a constant from the derivative is the same thing as subtracting a linear function from the overall function. So what we're going to do in the proof, define L of x to be f of b minus f of a over b minus a times x. Okay? Oh. Okay. Oh, right. All right, fine. So not quite. Right. Okay. So L of x is supposed to be the, let's see. Yeah, let's say this. Yeah. So it'll be like f of b minus f of a over b minus a times like x minus a plus f of a. Yeah. So then L of x, so the graph of L of x is the dotted line in the previous diagram. All right, so if we go back to here, L of x, so this is the graph of L of x. Okay. So clearly L of a equals f of a, right? Yeah. L of b equals f of b, and L prime of x is easily shown to be f of b minus f of a over b minus a for all x in AB, right? So now take g of x equals f of x minus L of x, and note, okay, g of a equals f of a minus f of a, you know, L of a is f of a, right? So g of a is 0, g of b is 0, and g prime of, well, okay, yeah. I'll get to that in a sec. So g of a is 0 and g of b is 0. Then Rolle's theorem tells us that there exists an x in AB such that g prime of x equals 0. But then for this x, f prime of x minus L prime of x equals 0. So f prime of x equals L prime of x, which equals f of b minus f of a over b minus a. So that completes the proof, right? So yeah, that's what this L of x does. I don't think you actually have to make it match up the values here. I guess it's just easier to show that g of a equals g of b if that happens, because they're both 0. I'm pretty sure they'll both be equal no matter what, but anyway. Yeah, so So that's the proof. So what we did was we sheared the graph to turn it into Rolle's theorem. Okay, so this actually brings me to the lecture question. So lecture 22, question 1. Suppose f is continuous on AB, differentiable on AB, the open interval, and f of A equals f of B, and there exists a C in AB such that f prime of C is less than 0. Then must there exists a D in AB such that f prime of D is greater than 0. Okay, so you can resolve this question just using what we've talked about so far, i.e. no integrals, no integration allowed, okay, for this entire section here. We're not going to talk about integrals. But yeah, so, do think about this yourself. And remember to include your answer with your homework. Okay, so the answer is yes. And here's how we can see. So if f prime of if there exists a C such that f prime of C is less than 0, then f cannot be constant. So f must achieve either a max or a min which is not equal to f of A or f of B. So like that loss of generality, suppose x naught is, or D, or yeah, x naught, let's say x naught is a point in AB such that f of x naught is a max, or is the maximum, and f of x naught is greater than f of A and f of B. Then there exists a D by the mean value theorem, right? There's a D in a x naught such that f prime of D equals f of x naught minus f of A over x naught minus A, which is greater than 0. Okay, so actually, so let's not even do this without loss of generality. Let me also show you the case for a minimum, right? So otherwise, suppose there exists an x naught in AB. Oops. Or well, yeah, such that x naught is minimal on, sorry, f of x naught. Did I say x naught is minimal? Yeah, f of x naught is minimal on AB, and f of x naught is less than f of A, which is equal to f of B. Then there exists a D in x naught b such that f prime of d equals f of b minus f of d over, or sorry, x naught over b minus x naught, which is greater than 0. So in either case, right? So in either case, there exists a d such that f prime of d is greater than 0. Okay? Right. So yeah, this kind of is in line with our intuition that for in a situation like this, where f of a equals f of b, then the average slope is 0, right? So if there's a place where f prime is less than the average, then to balance that out, there has to also be a place where f prime is bigger than the average. So that's actually true. Like you could generalize this to, I just did it with f of a equal to f of b to make the algebra simpler. But you can easily generalize this to a situation where basically you're saying, suppose there's a c such that f prime of c is less than the average slope. Then does there exist a d such that f prime of d is greater than the average slope? And the answer will be yes. And you can actually prove that situation just by transforming it into this one, the same way that we transformed the mean value theorem into Rolle's theorem in the proof. So anyway, that is all for this video. In the next one, we'll look at some corollaries about, that basically are about when a function has derivative 0, or when two functions have the same derivative, what can we say?